Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about geothermal heating and cooling. So let's dive right into it. Now first we have to understand what we call basically air conditioners, refrigerators, coolers, things of that nature. They are generally heat pumps. That's one thing we have to understand. Now we need heat in winter, that's obvious, and we need to remove heat in summer. This is one crucial aspect that you must understand. There is no such thing as cold. There is only heat or a lot of heat, or you have less heat. So that's all you have to understand. There is no scenario where it's like there is a cold, there is no negative energy. All you just have is like very little energy or a lot of energy. And heat pump can move heat. That's the whole point. That's why we call it heat pump. Ask any of your engineering friend, they will specify it. And what's the unique thing about it is very simple. It can push heat in hotter medium. What does that mean? That simply means if you paid attention in school, you must have studied this one simple thing. Energy always want to go from higher concentration to low concentration. What does that translate to? So let's say you have a one temperature reservoir that is 50 degrees Celsius, another that is 30 degrees Celsius. Heat will always, under all known science, will always try to go from 50 to basically 30. So that's normal. That's how things happen. That's why over time your house heats up during the daytime and then it starts to cool down during the night time. That's all is happening. Basically, if ambient gets cold, your house dumps the heat from its hot brick walls to ambient environment, and if the ambient environment is hot, the energy from ambient air goes into the brick walls. So that's normal heat flow. That will happen without you doing anything. But a heat pump is unique because it has the ability to pump in the reverse direction. Think of it this way. You have a water well that has water in it. You have a water tank that is somewhere on the top. How the heck water goes from that low potential to high potential? You use water pump. Same thing happens here. Basically, your evaporator, condenser and compressor, all they are doing is some way to figure out how to pump heat from cold temperature to hot temperature. Because if you want to pump heat from basically hot to cold, you're doing it wrong, because it will happen automatically. You don't even have to do anything. All you have to do is just connect it. Basically add a heat pipe. Basically how you have basically laptop coolers, CPU coolers, they have heat pipe. To do it more efficiently, that's all you have to do, because heat will naturally go there. So all we are doing to basically achieve lower than ambient temperature, basically assume this is your room is at 30 degrees Celsius. You don't want it to be 30 degrees Celsius, you want it to be lower than ambient. So basically you want to cool this puppy down to let's say 20 degrees Celsius. You need to use a heat pump. Only then it can go down. Then you can pump the heat from basically this low temperature to high temperature, and this temperature will end up like temperature minus whatever temperature you remove. That outcome is cold. So that's how heat pumps work. Now, one thing, one word that you will hear often again used around these things, that is called COP or COP, coefficients of performance. Now, this is very complicated and very simple also. So think of this way. In simplest term, if I have to explain, it exceeds 100% efficiency. Now, if you're like, dude, that physics does not allow that. Well, yes and no. This does work. This is real life, real reality. This does exceed 100% efficiency, but you have to calculate it differently. For example, let's say you are thinking about heating your room. You put 150 watts of heater element in your room. How much energy you gonna get out of it? Absolutely 100 and basically 150 watts of heat. Basically, if you put 1.5 kilowatt, you will get 1.5 kilowatt. This is one thing we humans do that is 100% efficient, is heating something. If you put 1.5 kilowatt of energy inside your room will go up in temperature by that amount. That's simple, done. Now here's the deal. What if I told you that you can use the same amount of energy, as in like 1.5 kilowatt, and you can dump 4.5 kilowatt into it? Like, wait a minute, where did that extra heat came from? That's why you have to understand this is a heat pump. You can take heat from cold area, aka your outside ambient environment that is cold in the winter, take that in and add the energy that you put into the heat pump itself, and then have the output. Your COP would be higher. So in summer times, your AC will consume, let's say, 1.5 kilowatts of electrical energy, and then it was gonna give you 3 kilowatt of cooling energy. So basically you put a 1.5 kilowatt, your compressor evaporator side went down in temperature, cooled the room down, it extracted 3 kilowatts of thermal energy. That 3 kilowatts of thermal energy got added to 1.5 kilowatts of electrical energy that was consumed by compressor, and then that whole grand total was dumped into the hotter medium, basically outside hot environment. And if you can reverse the cycle, basically all you have to do is just change the fluid flow. You will still have the same thing. Your heat will always add the basically the energy consumed by the compressor, and your cooling side will always reduce it. That's why, like, if you want to calculate the cooling COP, it will always be one lower versus heating COP. Heating COP, you can exceed one more. Now, what does that translate to? What does it mean for you and me? Simply put, if you had 1.5 kilowatts of electrical heater, which is very expensive to run, you can run like same 1.5 kilowatt and get 3 times the performance out of it. Basically it would be literally equivalent of if you had 2 more. That's how much that COP matters, because you're pumping heat rather than creating it. You can get more out of it. What does that mean? That simply means either you can run your 1.5 kilowatts of heater for less duration, because again it's producing a lot more heat, you can run it for less duration, or you can be like, hey, I'm using the same amount of heater, but I'm heating up a large volume of air. Basically, instead of a heater that could barely warm up your room, is can now easily heat up your whole home because of the high COP. That's the part that you have to understand. So COP in terms of heating, that's why we always get one more, and in terms of cooling we still get a bit more, and that's why you will never see anybody using Peltier coolers to run refrigerator or air conditioner, because Peltier does not achieve COP. They are barely at 1, not even 1, I'm talking like 0.4 or something like that. So that's the whole reality of it. Now why does this matter, and why this is this rating is not put on any basically air conditioner unit, refrigerator? They never say COP, this has 4 COP, 3 COP or something like that, because it's a dynamic system. Now think of it this way: what will happen if a water well that you are extracting water from goes down? Your basically pump has to do more work in order to pull that out. Same thing will happen with your compressor also. So if the temperature gradient, basically hot reservoir and cold reservoir, the greater the gradient, the more difficult it will become for the pump to do this pumping thing. So efficiency will go down, and efficiency will directly go down in COP. So if you are talking about, let's say your room is at, let's say 25 degrees Celsius, it's evening, and your outside temperature is 30 degrees Celsius, that's 5 degrees Celsius of gradient, and you want to cool your room down to, let's say 20 degrees Celsius. Your AC is like, bro, I got this, no, don't worry about this. You will barely hear your AC. It will turn on 1 minute, dumps the energy, no problem. Now let's talk about, let's say Indian summer. Our brick walls are heated up. That happens around 3 p.m. or something like that, and in this time walls are heating up. They are dumping energy inside the house without any concern, and outside hot air is around 50 degrees Celsius. At this point in time, your compressor could be like literally trying to achieve 20 degrees Celsius inside the room, while the outside is around 50 plus. That's a very large gradient. The energy requirement at that point in time will go up. What does that translate? That simply translates your compressor will not shut off. Your compressor is like a fixed power unit, so it's generally overpowered, and it always does on, off, on, off. Now if it's in like a very high load, it will remain on for longer. That's all it can do. So that's the whole point. So that's why COP cannot be put into a basically a marker, because they have to like, okay, COP of this air condition is like, if your indoor temperature is this much, indoor humidity is this much, outdoor temperature and humidity is this much, then you will get the COP. But again, those things are dynamic, they change. So inherently COP is not something that you can just like put on a system. You could have a sensor that can show you dynamic COP if you have weather monitoring systems, but it still won't be very accurate. So what does higher COP, basically if your air conditioner goes to, let's say 1.5 COP versus 2.4 COP, what does that translate? That simply means you have to consume less energy. Your power bill, air conditions are very heavy on energy consumption, and that is the primary reason, because most of the time the COP is not very high, because it's generally when you are forcing your air conditioner to work the hardest, when it's near impossible to dump the heat from let's say a room of that is like 20 degrees Celsius, that is your intended temperature, and the outcome is like somehow dump the energy from 20 degrees Celsius into 50 degrees Celsius. It's not very efficient. So that's why COP on those sort of time would go down, and you will literally feel it. Your air conditioner is like, wait a minute, the compressor is still making sound. Why it's making sound? It's like it's not going off. It's like it's trying its heart out. And higher the gradient, lower the COP. So if you are in a scenario where everything is calm, that's why many people try to run their air conditioner at night time. It's more efficient. COP is much more easier. The gradient is less. Let's say in India, it would be the outside temperature would be 50 degrees Celsius in daytime. It would be around 30 degrees Celsius at night time. So it's much easier on the air conditioning unit to dump energy at night time. So that's why COP is such an important factor here. Now we add soil to this mess. Right now all we are talking about air exchange medium. Now if you talk about soil, if you dig deep into soil, as in like anything below 3 meters or 10 feet deep, soil at that point in time remains constant in temperature. Now it will have a temperature gradient. It will have little will go up, little will go down, but it will be very smooth. It will not be like, okay, let's say you will have heat waves. You will like literally do this temperature went up. Your soil will not care. Like specifically if you go deep enough, it will simply not care. You will barely notice whether it's summer or winter. The temperature at the depth gets almost locked. It's like there is a lock there. Now there is a depth that people living in northern climates, they have to figure out that there is what we call frost limit. Basically, ground freezes at that point in time. Uh, Basically at that height. If you go below that, then it's like it does not care. So if you go deep enough, let's say you reach a point where it's 10 degrees Celsius in winter, it does not matter whether it's like a minus 10 degrees Celsius or minus 30 degrees Celsius on top. It does not care. It will remain at 10 degrees Celsius. It will not go below that temperature. And in summer, when let's say outside temperature can go up as high as 50 degrees Celsius to 60 degrees Celsius, the soil, will barely cross 30. Barely, like it will simply not get. There is like almost a buffering kind of effect. And because of the mass involved, again, the soil is denser than air, it has such a mass involved that you can dump a lot of energy into the system before this system gets saturated. So this translates to, it's easy to pump heat in 30 degrees Celsius versus 50 degrees Celsius. For us, let's say we did a ground loop system. Ground would be, let's say, 30 degrees Celsius and our air is 50 degrees Celsius. The compressor would love to dump the energy into 30 degrees Celsius. Like, bro, I was made to this, I can do this efficiently. And if you try to force it to do 50, it will work. It does work. It's just like it will consume my electricity bill like there is no tomorrow. So that's the whole point, and that's why every Tom, Dick, and Harry wants to do this, lower power consumption. And because our temperature was going averagely up, like 50 degrees Celsius was a very high temperature. Like we had school closures when that temperature used to hit. Now it's like a normal temperature. Heck, some places in Bangalore is so goddamn hot that during evening time you will have heat wave coming from the giant concrete buildings. It's like, wow, it's like idiotically hot. I'm talking about like a 55 degrees Celsius air temperature, achievable around 3 to 4 AM, PM, pardon me about that. So soil, compared to that, it's super easy. Soil is like, bro, air condition is like, I got this. I don't even worry about me. I got this. Heck, you can run your air condition on inverter because it won't consume too much power. So what's the setup behind this? Well, it's very simple. All we want is winter in the summer, basically. Winter in the summer, summer in the winter. All you want is warm for the winter, cool for the summer. A normal AC is a by default heat pump. It's just one way heat pump. So whenever people are talking about heat pumps, that simply means an engineer put a little extra valve that allows the coolant flow to be reversed, and that creates what we call the heating effect, and ground loop acting as a heating. Now this is the most expensive part about this whole system. Till this point, it's just a normal air conditioner. You don't have to think about it. Or worst, it could have one extra unit of let's say heat exchanger, but you have to somehow get to the ground thermal mass. The easiest way to achieve is horizontal loop. If you have a lot of land, contractors will come there, dug up a tunnel node, as in like a ditch. Now depending on the money you are spending, the ditch will be deep. Like generally people will say do not go anything less than, let's say, 3 feet. And if you have the ability to go deeper, because the deeper you go, specifically in the colder climates, you want to be damn sure that no matter what happens, the ground loop does not freezes. So in very cold places like Alaska, things of that nature, you have to go really deep. In those situations, you will have horizontal loop. That is, there is a complete pipe that is having your coolant running through there. Coolant is generally water plus glycol. Now people also add basically antifreeze to that, simply because there is a place where it's transitioning from the frost line. So if you do not have antifreeze, it can freeze up in that area. So this place will be liquid, this will be frozen, so it will almost seal up the system. So generally you have to have, there is always a recommendation to have a bit of antifreeze. That's not something that we Indians have to worry about, but you get the point. That's why, like, you will always say, okay, if ground is never freezing, why the heck we want to add antifreeze? It's just that it has to go through that plug, and if for some reason, let's say your liquid pump breaks for some time, you do not want it to instantly freeze. So the tubes with water and glycerol, that's your heat sink medium. That's basically dumping the heat energy from one medium to another. In winter, you will extract heat energy from some basically soil, and in winter, you're gonna dump heat energy into the soil. That's all you are doing. And you have to figure out a way to connect the condenser. Now, if you some companies, all they do is basically they have the condenser unit in a oil tub, and there is another heat exchanger. That's much easier to connect compared to some systems which have like liquid directly going through the refrigerant line. Now that heat exchanger is very expensive. Many companies do that, but it is expensive to do. So you can have different systems depending on your cost and money and all that jazz. Now that's all you have to do. Inherently, it's one of the simplest things. Just somehow figuring out a way of digging horizontal loops is the expensive part. And because you do not have a lot of horizontal spaces nowadays, because we are packed so closer to each other, and if you are talking about a urban area, you will rarely have any space. People are trying to do vertical, basically go down rather than sideways. As how deep? Generally you are talking about 200 or 300 feet. So it's basically more or less the same equipment used for boreholes. Just same equipment is utilized for this system. So only the difference would be, instead of water, there will be a loop of coolant running through it. Coolant as in water plus glycol and bit of antifreeze. So that's the setup. Inherently simple system. So what we can expect in the future? Now you think we have learned this the hard way, that it's much better to pump heat rather than to create it. It's like a 1.5 kilowatt of heating element is awesome, but if it consumes 1.5 kilowatt and gives you 3 kilowatt or even 4 kilowatts of thermal energy, that's awesome. That's like, why would you not do this? Like, and if you have the equipment, aka if your air conditioner is already built, if it already has a compressor, if already has a 2 heat exchangers, why would you not add just one valve that allows you to do that? And it's doing that right now. Heck, even my air conditioner, as in like Blue Star air conditioner that I have, has the switch for it, the thermal mode. It's just that from the model it's not there. So like, if we had spent a bit more when my father bought it like 4 or 5 years ago, we would have gotten that heating unit. Right now more and more heat basically air conditioning unit are coming with that function. So same way we are reaching there, over time people will reach to a point where it's like, dude, the energy bill is so goddamn high that I have to utilize basically ground loop, otherwise the COP is so low that it's like almost like, to cool 1 kilowatt of getting 1 kilowatt of cooling, I have to spend 1 kilowatt of electrical energy. At that point it's just unbearably expensive to do. So cooling with low energy is cool, everybody likes it. And the primary reason why not every Tom, Dick and Harry is doing is high capital cost. Like digging these trenches and pairing these pipes are not that expensive. Water and glycol, they are not that expensive. But having the space to do these things, be the manpower required to do these things, they do add up. And the units, because they are not sold in like, large masses, it's a bit more expensive. And the people who are trained to do this sort of thing, they are expensive. But even in India, like there are basically colleges, universities that are utilizing the system, because I have provided a video down below and you can check it out. It was kind of old system, like 2014 to 2017. They started with 250-ton cooling unit, and then now they have moved to 300 tons of cooling unit. It saves them a lot of electrical energy. Like literally, they were saying around 10,000 electrical units per day is saved. Like they took a big risk because the capital cost was very high, but over time it's like it paid off. And when you're talking about residential system, people are saying like generally return on investment, basically by the time you have saved enough money where it's like worth it to do it, is generally around 10 to 12 years. And because the central air conditioning unit that every house nowadays are getting, they are long-term equipments. They are supposed to running for 20 years, 30 years or something like that. So in those sort of scenario, utilizing something long-term is wise. And every Tom, Dick and Harry likes the idea of saving money. It's like, you don't care about the environment, you should not even give a damn about whatever. It's just like, I should not need to sell you, hey, this saves the environment. I have to tell you with this, hey, this saves you money. Every Tom, Dick and Harry will do that, and people already started to do that. That's why I specified it. Even in India, college and university, they have the big check to write the capital cost, but more and more interest are being created to create this sort of small scale system which can be integrated in homes. And because people are now utilizing normal borehole technology, most equipment is already there, rather than requiring new technology. So right now the primary problem is that capital cost. Once it's been taken care of, we can achieve amazing things. Basically, imagine an air conditioner that runs at like a COP of 3 all year round. That's awesome. Like in winter it will go to 4. So that's amazing. At that point in time, you will have lower energy consumption by city level, and you will not also cook the ambient environment. Basically, if you hate your neighbors, put your condenser unit directly blowing hot air into their wall. Don't do that. That's very rude. So this was my presentation on basically geothermal heating and cooling. Hopefully you have liked it, learned from it. In that case, please give the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.